people still getting beers, but we're going to go ahead and get started. So tonight we have two great speakers who are going to talk about pulsars and gravitational waves. I'm a gamma reverse astronomer, so this is very interesting to me. I'm very excited to hear these talks. So our first speaker is Dr. Mikel Falxa. Let me get his bio. Okay, so Dr. Falxa is a postdoctoral researcher at the Laboratory of Physics and Chemistry of the Environment and Space Orléans, working on the detection of gravitational waves, small ripples in cosmic space-time through precise timing of pulsar observations. So tonight he's going to talk about a collaboration called PTA, if you're familiar with that. So we'll go ahead and switch the slides. Just a minute.
Ooh, spoiler.
Okay, and we'll have Dr. Falxa take it away. Please give it up for me.
Hi everyone, thank you very much for the organisers to invite me, for everyone to come. You hear me well? It's all right? Okay, good. So, I'm Mikel Falxa. I'm postdoc researcher. Right now I'm moving in Paris, but now I'm going to Milan. That's another story. Anyways, today I'm going to talk to you about pulsars, and especially this title, When Pulsars Are Off Beat. What do I mean by that? Well, I hope by the end of the presentation you will know. So, over there. Okay, so I want to give first a brief introduction about all the things you need to know to understand really the topic of pulsar timing array, because that's going to be the main topic. So first I'm going to give a brief introduction about general relativity and how gravity is described in general relativity to understand what a gravitational wave is. And then finally, after this, I will just give some introduction of what black holes and pulsars are, where they come from. And finally, we'll talk about the meat of the topic, the meat of the subject, which is pulsar timing array. So, in general relativity, which is famous because that's the theory of Einstein, we have space and time, which are an inseparable entity, which we call space-time. Basically, that's the scene, the stage where all the physics happens. And the main teaching of general relativity is that this space-time is not still. It can curve around with the effects of matter, the distribution of matter, the distribution of energy. So, if I put a little star over there in the middle, what it's going to do, it's going to curve this space-time. And because the space-time is curved, the trajectory of bodies around the space-time is going to be perturbated. And literally, that's the main equation of general relativity. You don't have to understand the math that's happening there, but basically, really, what it says is curvature equals matter. So basically, the distribution of matter tells space-time how it will curve. And this is an effect that is very weak. So usually, we'll just feel the effects of this gravity, because this is how gravity is described now. And you need very massive objects to feel really this effect of curvature. Now, this was when there was a static body in the middle of space-time, in my little sheet of space-time. But if I have a very specific configuration, for instance, I have two black holes orbiting each other, now the source is going to be dynamic, it's going to depend on time. As a result, the curvature that this system produces is going to be very different. It's going to propagate through space-time, and you're going to have these curvatures that propagate at the speed of light, and when they pass through an object, they change the measure of distance. They change, really, 1 centimeter is not worth 1 centimeter everywhere in space. That's because if a gravitational wave passes through, as you can see here, you've got a ruler. Of course, the effect is exaggerated by a lot, but this ruler is basically getting stretched because of the passage of the gravitational wave. And this effect is really, really weak. You have in the order, the amplitude of the gravitational wave, you can find many in the order of 10 to the minus 21 to 10 to the minus 14 for the loudest we know. And basically it's an effect that you feel at the level of really microscopic atomic nucleus level. So this is a tiny effect. And if we want to see the effect of gravitational wave, the objects in the middle have to be very, very massive. What? Oh shit. Okay. Right. So, the massive objects. How do we produce massive objects? So, brief summary for those of you who may not know. Stars. The stars, basically like the sun, all the things we see, they're huge balls of gas illuminated by nuclear reaction. So how do they get illuminated? It's because there is, so you have several sizes of stars. You've got tiny ones to huge ones, and what happens is that this huge ball of gas is collapsing by its own gravity, its self-gravity, and it collapses so much that in the center it gets really hot, and nuclear reactions start to ignite. And because nuclear reactions ignite, they start to counterbalance this gravity. And basically, while gravity is pulling inwards, nuclear reactions are pushing outwards. And because of this effect, the nuclear reaction, they need fuel. The stars, they're made of hydrogen, helium, you name it, many components. But once the fuel is done, the star will die. And how does it die? It's basically now gravity wins over the nuclear reaction and it can explode. But this is only if the star is very massive. And this is what we call a supernova. If you have a very tiny star, like the sun, as you can see in the classification of stars, is actually quite tiny. You've got really huge stars over there. It's going to do just a planetary nebula, which is a very mild explosion. It's not like a supernova. So basically, when it's done, boom, it explodes. So what we're interested in here is the supernova. Why? Because when the star collapses, it concentrates all the matter in its center. And usually what happens is before the explosion, it will create a very dense object, a very, very dense object that will keep the rotation of the star in a very little volume, so it will spin around very quickly. This is what we call a pulsar, and this is a star that is made of neutrons, which is very dense, highly magnetized, and spinning very, very quickly. And it's very little in the sense that it's only 10 kilometers in diameter. It's kind of small, but it's extremely dense, like just a spoonful, a little. So basically, just a spoonful of pulsar it weighs like 1 billion tons. So it's very, very dense. We can't even comprehend how dense this is. And see, the image of a supernova I was showing. This is a real image, by the way. If you watch it in X-ray, you see all the very powerful winds of charged particles, electromagnetic radiation. In X-ray, you can directly see the effect of this pulsar in the middle of the supernova. So we do see them directly. Actually, sound. If you want to listen to a pulsar, that's what it would sound like. It's horrible, but it's very fast. So you can hear. This is just the electromagnetic radiation that was converted to sound. And that's what it gives. So imagine that's at every you have one turn. And this is the size of the city. Imagine like the city of Paris that is spinning at that speed. That's spinning really fast. And okay, thanks. And you have other type of objects that can be created by the collapse of stars, like that very dense object, even denser than pulsars. And these are black holes. This is when it gets so dense that the gravity is so strong that even light cannot escape. The curvature of space-time I was showing in the beginning is so dense that light doesn't escape, so it becomes black. And this black region is what we call the event horizon, the limit between the outside and the inside of the black hole. But still, the black holes that come from star collapse, they're usually kind of small, little baby black holes of some solar masses. What I'm going to talk about today more is supermassive black holes. So basically, black holes that exceed 1 million times the mass of the sun. So basically, 1 million times bigger than the sun. They're in size, they're like the size of the solar system. They're extremely massive. And this is the kind of black hole that we find in the center of galaxies. The picture you have on the left is actually a real one. So you see that's the limit between the inside and the outside of the black hole. The black dot in the middle is actually what we call the event horizon. And this is kind of crazy that we really can see with their eyes. And these black holes, usually they were born in the very early universe, because we already see galaxies in the early universe, like less than 1 billion years after the Big Bang. And it's kind of hard to know how they formed. And one of the ways to form them is through galaxy merger. You have other galaxies and they merge together and they create even bigger black holes. But the thing is, we've never seen this. We've never seen that effect of merging black holes. So here you can see images of galaxies merging together. And when something like that happens, we should form a binary system of such massive, supermassive black holes, but we've never seen them. And the thing is, can we detect the gravitational waves of binary systems of supermassive black holes? Is this possible? And that's the question we want to answer. So there was a very clever idea that was proposed long ago by Sazin in 1978, which is to use pulsars to detect the gravitational wave from supermassive black holes. Because basically, if indeed we can form binary systems of supermassive black holes, we expect to have plenty in the whole universe, and each of them will be emitting gravitational waves. And the sum of all the little binary black holes, supermassive black holes you will have in the universe, they should produce a very low frequency noise, which we call a gravitational wave background. And as a matter of fact, we could, according to the idea of 1978, we could detect the gravitational waves coming from these supermassive black holes using pulsars. So this is the whole idea of the pulsar timing array, because now it became a worldwide collaboration. You've got people working in several countries in the world, internationally, to try and make this idea work using pulsars. But how? Basically, this is how a pulsar would look like from Earth. When you look at it, we see them in the radio frequency band, so we monitor them with radio telescopes. And basically what you see is that they emit light in beams of radiation like that, and they spin. So very quickly, this is very slow for the illustration, but much quicker. And we use very old pulsars that calm down in a sense, because they're more stable, they're very stable old pulsars. And the thing is, it does this lighthouse effect. It's really like a lighthouse that's spinning around and emitting flashes of light. From Earth, we just see flashes of light. And that thing, the interval between two flashes of light is extremely stable. It's actually even as stable as some of the atomic clocks that we have on Earth. It's extremely stable. And thanks to this stability, to this precision, we can use them as clocks, cosmic clocks if you want to make it sound fancy. But basically what you want to do is that you use this precision timing measurements to detect the curvature of space-time. If there is a gravitational wave that is passing through, it should perturbate the time of arrival of this pulse. It should perturbate the spin rate that we see from Earth. of this pulsar. So now, that would be an illustration, okay? Because the pulsar is very stable, we're on Earth, and the pulsar is sending pulses of light. So if indeed we could see this pulsar, and it is stable, it is without any perturbation, we could predict how the pulses will arrive. So basically, in terms of tempo, let's say, you could hear the pulsar and match a metronome to the pulsar. Matching the metronome is what we call a timing model. We've got a mathematical model to predict the time of arrival of the pulse. And if everything is okay, we could set the metronome right to the pulsar. Actually, well, let's skip. I wanted to make some sound, but it's all right. Okay, here. Press this one. That would be... No sé... Bueno, ya. No, pero no pasa nada. Está bien. Y... So, well, it's all right, it's all right. Anyways, if indeed the metronome, we could set the metronome to the pulsar, that's what we would see, and everything is okay. But if there is a gravitational wave that is passing through this pulsar, between pulsar and Earth, you can see that the time of arrival of pulses will be contaminated by this gravitational wave. It will change, it will get modulated. And because of that, our metronome, we cannot set it to the right frequency of the pulsar, because the space-time is curved because of the gravitational wave. And because of this curvature, we will feel a difference between the timing model, so basically the metronome, and what we actually observe. And in this difference, we will have the information about the gravitational wave. So basically, that's what I mean by pulsars are off beat, because they don't beat at steady tempo anymore. If there is a gravitational wave that passes by, it will change the tempo and it will change the beat, and the pulsar will be heard off beat because of the gravitational wave. So that's why it's not really quite the tempo we like. Until now, I was just showing one arm pulsar Earth, but the pulsar timing array, as the name indicates, it's basically going to be a combination of many pulsars that we monitor at the same time. And because we monitor at the same time all the differences in timing of the pulsars, all the modulations of tempo of all the pulsars, we have mathematical models that can predict if this perturbation is coming from a gravitational wave. And as a matter of fact, with the EPTA collaboration, which is the collaboration on part of basically the European pulsar timing array collaboration, we've been looking for this signal. Okay, these are the telescopes, all the countries that are involved in the collaboration. We're here, and there's UK and everything, but still, Indian people, they join also the collaboration. We've got a lot of data, and last year we published a paper all together to show this. So, what does that mean? It's really hard to explain, but basically it means that we do see a signal. If it is a gravitational wave, it should follow this green curve. And it actually does, kind of, within error bars. But the only issue that we have is this. This is the plot that shows the spectrum of the signal, which is the shape of the signal that we see. And actually, if it were really coming from supermassive black holes, we would expect to be here, this point to be here, but it's there. So there are many things that we don't understand still. But we can say with confidence that we do see a gravitational wave signal, strong evidence for this gravitational wave signal, but we still don't know exactly the origin of the signal. The main candidate is supermassive black hole, okay, the population of all the supermassive black hole binaries in the universe. But there are plenty of other origins, like basically we've been working on single binary black hole that could emit gravitational waves, strong gravitational waves, or cosmic strings, or inflationary gravitational wave background. I'm just throwing words so you could do your homework if you're interested in that, because I'm running out of time anyways. But yeah, we still have a huge work of interpretation that has to be done, because we don't know yet exactly what we're seeing, but we do know that there is still evidence that this is a gravitational wave signal, and this is really cool because people have been working on that for 20 years now, and finally last year we've been seeing stuff. So it was a kind of cool discovery, and it was cool to arrive at the right time, because that was the end of my PhD. Well, conclusion. Basically, we do see we see a signal in the European data. For those who know frequentist analysis, we have 3.5 sigma confidence for this signal. So it's still not 5, but still it's kind of high. Main candidate is the population of supermassive black hole binaries. And then, still impossible to determine the exact origin of this gravitational wave signal. And in the upcoming years, right now actually, we're already trying to put together all the international data we have from all the collaborations in the world, so we could actually, have a more sensitive data set and see the signal more clearly. And this is I hope next year, maybe in 2 years, we're going to have finally the 5 sigmas, the confidence to say we know what we see. And thank you for your attention, but just for the last slide, just to show that I was talking on behalf of the European collaboration, but the American collaboration and the Australian collaboration, they do see, independently from us, they do see the same thing. So that's also builds up the confidence. So that's why we're working right now to put all the data sets together, and hopefully we'll see something in the upcoming years. Right, thank you very much. Sorry.
Okay, we're going to do question time. So if anybody has a question, please raise your hand, and I think we have a second microphone that we can bring to you for your question.
You have a question?
Yes.
Okay, great. Does anyone have a question? Please raise your hand.
Thank you very much for your talk. Very nice. The question I have is maybe a bit naive, but when the gravitational wave arrives to the Earth, it doesn't also distort our measuring date the same way it distorts the space-time. So we shouldn't really see a difference. If the gravitational wave is distorting the space-time, it doesn't also distort our measuring system the same way. So we shouldn't see any effect.
Right, I see. Yeah, because what I can say is the effect of the gravitational wave is just not what we see on Earth. The whole signal is actually the difference between what is felt at the pulsar and what we see on Earth. If you will, it's the oscillation of the whole arm, Earth pulsar, the whole axis. This is what gets perturbated. It's not just because we're all bathing in the same gravitational field that we don't see any difference. We have to see the difference. And on top of that, it depends on the direction. If you have a pulsar there, a pulsar here, a pulsar there, the effect that you feel is different. So it depends also on the angular separation between pulsars and the position in the sky. Actually, I didn't show, but this plot is the correlation pattern. This is what we look for, what we're looking for. And basically, if you will, it's the correlation the pulsars should follow according to the angular separation. See, if they're very close in the sky, they should see the same signal. The more apart they are, the signal should be different. You see? I don't know if I answer your question. Yes. Okay.
Thank you for the talk. It was really nice. I have a question about the non-linear. So, what is actually the frequency range for the pulsar signal? What is more or less the frequency range of the gravitational, perturbational, noise? And how difficult is it to synchronize all the telescopes in order to be able to show the observatories?
Right. So the gravitational wave signal, I didn't mention actually. It's right. It's in the nanohertz range, so it's extremely low frequency, like periods of 1 year. And the pulsar, the millisecond pulsar, so they go very fast. But the thing is, every point it comes from an observation of the pulsar. Every TOA time of arrival that we have, it's like epoch. It's not exactly just we take all the pulses, all the 1,000 pulses, in 1 second. What we do is that we observe the pulsar for an hour, and then we integrate from this time, and we take the average time of arrival, and we do this every week. So it's kind of a slow cadence. So the effect of the gravitational wave, really, that we feel is in the order of years. And then your other question was.
How do you do for synchronizing all the radio telescopes?
All right, to synchronize the radio telescope. So it's actually a bit challenging. We've had issues in the past with this, but basically they all have locally. They have atomic clocks. So they have very precise measurements of time. But then they're all synchronized to the GPS time, so they have a universal time, so we can all fix them together. Because yes, it's really important that they're all synchronized. So basically, you've got a measurement of time locally, but then you have to basically change your clock, adapt your clock, so they're all at the same time. But the official time is GPS time.
Yes, what is the tolerance of your frequency for the pulsar? It's pretty precise. What is the tolerance?
I don't hear, sorry.
La frecuencia del pulsar, ¿cuánto es más o menos la tolerancia que tiene?
¿La tolerancia de qué?
De la frecuencia la que te emite la señal, el pulso.
El pulso. If it's okay, sorry, yeah. If it's millisecond pulsar, it's like 200 hertz. It's spinning at 200 to 1,000 hertz.
Plus minus.
Plus or minus, it depends. For us, it's going to be plus or minus 100, I would say, because the thing is, we use only millisecond pulsars. Because if you will, they're very old pulsars, not new pulsars. Because the young pulsars, basically, they're all prone to glitches and quakes, dark quakes, and stuff like that. So usually we use milliseconds that calm down, and usually they have a companion, which they steal matter, they steal angular momentum for this companion, and they get re-accelerated. This is why they're really fast and really stable, thanks to this. But usually it's more or less, say, 200 hertz.
Okay, I think we'll just have one more question. One more question, but I encourage you to come and talk to Mikel afterwards if you have a question. You might be able to hear better.
I just want to know if I can achieve the gradation. I just want to know if
You can. Where? No. The Hellingsdown curve. Not necessarily. If you have some theories of gravity, basically, where you have other polarization modes, like maybe massive graviton or something like that, you're going to have other polarization modes. And if you have other polarization modes, then this Hellingsdown curve is changing, because this comes only from the, for those who know gravitational waves, from the standard plus cross polarization. Thank you for your question.
Again, I encourage you, if you do have a question you want to ask him, he will be here tonight, so please come up and ask him any question that you have. We're going to take a break for about 15 to 20 minutes.
That's good, man.
We'll change the slides and get ready for the next speaker. So go ahead and get a beer, and we'll see you at the top.